Hi guys, I am Nimish Vikas and I'll be teaching you ionic equilibrium. It is one of the most interesting topic in physical chemistry. It can be tricky at times, but if you master it, you'll love solving the problems and you'll feel like king of physical chemistry if you get it all right. So let's start learning each and every part very carefully. Understand each and every part because all of it will accumulate into quite interesting questions. And as I said, those would be fun doing it. So, what is ionic equilibrium about? Ionic equilibrium is about aqueous solutions, particularly ionic solutions. So, solutions Aqueous solutions can be categorized into two kinds. One is electrolytes and then non-electrolytes. So we have electrolytes and non-electrolytes. Now, as the name suggests, the historic meaning of electrolyte would be a solution which is able to pass electricity, and a solution which is not able to pass electricity are non-electrolytes. So that would be, I guess you would know it, say a sugar solution, glucose solution, urea. These dissolve in water. They are aqueous solutions. They dissolve in water. How would glucose dissolve in water? So glucose has several OH groups which can be polar. So it has got several OH groups which can be polar, and if you have a polar compound, then water is a solvent for polar compounds. You will be doing that in your organic chemistry a lot. So water is able to pull away the glucose molecules from the rest of the glucose. So water is going to pull it off, and that water surrounding a glucose molecule carrying it all around is nothing but the solution of your glucose. Same with urea. So these compounds must be polar and hence they are soluble in water, but they are not electrolytes because they won't be able to conduct electricity. So Faraday was the guy who was doing experiments on conduction of electricity through your solutions, through your aqueous solution mainly, and the charged particles which is carrying the electricity, which is helping to conduct electricity, he coined the word ion for it. So that was given by Faraday. That's right. And then these electrolytes, so of course they are able to conduct electricity, and the reason is that they have got ions. So electrolytes also, I can say, can be of two kinds. One is strong electrolyte, and then the other one would be weak electrolyte. So as the word says strong electrolyte, what can it mean? It means that the substance when dissolved in water is going to produce a lot of ions. So those would be your salts which readily dissolve, you know them, all salts. Then you'll have strong acids, you'll have strong bases, alkalis. So these are your strong electrolytes. So they completely dissociate, they almost completely dissociate when dissolved in water. So they produce lot of ions which are able to carry the electricity. By the way, carriage of electricity is no longer the modern definition of being a strong electrolyte. So I'll just put in another one over here a bit later. Let me just cover this weak electrolyte. Let me just mention few weak electrolytes. What would be a weak electrolyte? Weak electrolyte are substances when dissolved in water, or it's a solution which is having not those many number of ions. The molecules have not dissociated into ions, and the molecules have remained as intact molecules, non-charged molecules which cannot carry electricity for most part of it. So These would cover your weak acids. I'll name a lot of weak acids. You'll have your weak bases, weak acids, weak base. These are your weak electrolytes, and this chapter ionic equilibrium will be dealing, mostly the bulk of this chapter will be dealing with weak acids, weak bases, such that equilibrium is formed. If I dissolve this in water, what is going to happen? It is going to split fully and there is no equilibrium. It is a one-sided reaction. All of it I'm going to write it, so don't have to worry about it much. I'm just giving you a perspective. I'm giving you the idea what is going to happen in this chapter. So we are going to deal with these guys. I'll just name one, say weak acid CH3COOH. This, when dissolved in water, say 1 liter 1 mole was dissolved, so it's a 1 molar solution. Like this 1 mole is not going to dissociate fully. It is only going to give some amount of CH3COO minus and obviously the same amount of H plus. So this forward reaction is a very not a very strong one. It is mostly, if these are formed, they are tending to go backwards. So we'll have signs like this. We'll have a double arrow sign in most of the equilibrium equations. What we'll be writing, signs like this. So it goes forward and backwards. When I'm going to write the dissociation of this, I can't write that sign because it will be mostly forward. So an acetic acid will be learning the values, the dissociation constant, which will tell you how much it dissociates. So it is like mostly 95% has remained intact as the molecule itself. It's not a precipitate, so I will write aqueous over here. So this molecule is being carried by water all around, but the water is not splitting it into this and this. Only a small part, say 5% of it, is getting split into that and that. So that is a weak acid. Similar would be the case with weak bases. So these are weak electrolytes which are unable to split. So under strong electrolyte, I'll just put a controversial one. I will put it in slightly different color, AgCl. Now AgCl is also a strong electrolyte. Why would that be? Why I'm so much concerned about this salt? All salts I'll put under strong electrolyte. Now AgCl is a sparingly soluble salt. It doesn't dissolve. We are talking about aqueous solutions, the things which has dissolved. So if I put 1 gram, 10 gram or whatever amount in water, in say 1 liter of water, very minuscule amount of it is going to dissolve in that water and the rest is going to remain as precipitate. Now it would be solid, but the part which has dissolved, AgCl, solid, when it has been put in water, if I dare write AgCl aqueous, now what does it mean? It means that a single molecule of AgCl is being carried by water. That is not true ever. You don't have a single molecule of AgCl being carried by water. Your water, say these are water molecules. Water is not surrounding a AgCl molecule. We already know that ionic compounds don't have molecules as such like that. It is not a covalent compound. You don't have molecules defined like this. It can be n times that. Anyways, so this is absurd over here. So if AgCl from the solid state has been ripped by water and it has dissolved. So the part which has dissolved is completely becoming Ag plus and Cl minus. The part which has gone into the solution, this is your aqueous. Cl minus is being carried by water all around, and your Ag plus is being carried by water all around. Your negative end of the water is sticking to your Ag plus, your positive end of the water is sticking to the Cl minus, and this is the dissolved part, not this. So if you have a solution of AgCl. That means if it is dissolved, then whatever part is dissolved, how much ever low it is, whatever part is dissolved will fully dissociate. So it is, if I say a strong electrolyte is what fully dissociates when dissolved, I'll write it. What So if I say a strong electrolyte is what fully dissociates when dissolved in water, then the sparingly soluble salts will also qualify as strong electrolyte. And if I go by the definition of how well it is, how good is it a conductor of electricity, then the sheer number of ions being so less would disqualify it uh, for being a good conductor of electricity or being an electrolyte in that case. Okay, so we are not qualifying it as a good electrolyte because it conducts a lot of electricity. It doesn't, because your Ag plus is too less, your Cl minus in the solution is too less, so it is mostly as precipitate, and your water is, the water alone is not a good conductor of electricity. You'll have to have ions which are going to conduct. But if I talk in terms of how much of the thing dissociates as a solution, then this glucose doesn't dissociate at all, non-electrolyte. You have your we have our weak acids and weak bases which dissociate a bit, maybe 5%, maybe 10%, maybe 2%. So those are weak electrolytes, and then these dissociate fully. Salts when dissolved dissociates fully. So I hope you got the point. So I'll just name few weak acids, weak bases. I'll name some electrolytes so that those terms might be coming in the chapter again and again, and you should get familiar with them. So I'll just clear the board. So hi guys, I have listed a bunch of strong electrolytes and your weak electrolytes over here. So in strong electrolytes, we have strong acids, strong bases and salts. All ionic salts will qualify for strong electrolyte, how much ever they dissolve. So your strong acid, your perchloric acid, one of the strongest, it furnishes H plus ions in abundance. I mean, all of it will be giving you some ionization constant values, Ka values, and that you'll be learning later. But just to give you an idea, just to give you, if some numbers make sense, then the K value for this would be in the order of 10 power 10. It gives you, it shows that it almost dissociates fully. And then we have your Hi, HBr, HCl, H2SO4, all these industrial acids are the HNO3. And then if you have a protonated aldehyde or a protonated ketone, this is a protonated aldehyde made for you. Protonated ketone also, you have that's a ketone, and if it gets protonated, so you have H plus attached to it, sorry, H attached to it and plus over here. So this is also highly acidic. Very easily it will give away the H plus. That is what qualifies this to be highly acidic. Protonated carboxylic acid also, it is going to give away the H plus. Your carboxylic acid, say C double bond O and COH, so it is going to give away the H plus. When I say it is going to give away the H plus, it is going to give away this one, not this one. This one is not going to go away so easily when dissolved in water. So this guy is going to qualify it as a weak acid, but this one is going to give away. We don't have to worry about all this at all. I'm just listing a bunch of compounds just to give you an idea what are strong acids. You don't have to worry about the bonding part in this chapter at all. It is numerical based chapters, and all the facts would be given to you. So some idea of what are strong acids is what I'm trying to convey over here. If I write the K value for say Hi, this will also go in the order of 10 power 9. This might be also in the order of 10 power 9. This in fact is a 10 power 10. Your HCl is 10 power 7. Your H2SO4, it has got two H's, so the first H gets released very easily, so that's a 10 power 9. But the second H doesn't get released so easily. It is quite difficult to release the other one, so that when the second H is getting released, then the K value corresponds to 10 power minus 2. So that is in the weak range. Your HNO3, it is highly corrosive, and your again it is a 10 power 2 kind of K value. It is not as strong as these with respect to releasing of hydrogen, but it is obviously highly oxidizing. So it is if you see how much of damage an acid can do, then this qualifies as a very damaging acid. It is a strong oxidizing agent. So this guy is also a strong oxidizing agent, plus it is very easily releasing your H plus. So we are concerned with release of H plus in this chapter and not other aspects. So your protonated aldehyde is what is made over here, is also going to release the H plus very easily. Okay, then your strong bases are obviously the first group, hydroxides. So that is rubidium, cesium hydroxide, sodium hydroxide, potassium hydroxide. These are group 1 hydroxide, and this is the group 2 hydroxides. So group 1 and group 2 hydroxides would be strong bases. The solubility may vary, like this guy. If I talk about NaOH, it is like half a kg is soluble in 1 liter 1 kg of water, whereas this one only say 20 grams will be soluble in 1 liter of water. So the solubility is low, but we are not concerned about the solubility. I hope you have understood the difference between being soluble and dissociating. What has dissolved, does it dissociate or not? It will, because it is highly ionic. It is ionic because the electronegativity difference between the cation and the anion would be large, so it is highly ionic and it is going to dissociate. When I talk about other hydroxides, then the ionic character will decrease, and hence the dissociation will depend on the K value. So all those will be provided to you, but we don't have to worry, think one bit when it is when we are talking of alkali metals or alkali earth metals. Like if I say we have, is calcium hydroxide a strong base or not? Yes, it is. Whatever will dissolve, the dissolution is not that high. Whatever will dissolve is fully going to dissociate because it is ionic. Okay, then about salts. So any salt you take, you take uh, ionic salt, a crystal like KCl, you take sodium acetate, you take oxalates, you take complex salts, say potassium ferrocyanide, potassium argentocyanide. All these are strong electrolytes. You have your tetramine copper sulfate, that's a strong electrolyte. So all salts which are ionic, this and these are the cations and the anions form. These are ionic. Whatever is ionic is going to dissociate fully. Now HCl is also, it is not an ionic. These are all not ionic as such fully, but it is highly polarized. It is highly ionic, and hence it is a very strong acid. So here, if the ionic character decreases, like you see HCN, then your CH3COH acetic acid, then you have your phosphoric acid, hydrogen sulfide, HF, H2CO3. These are not that strong acids. These are weak acids, and if I look at the K values, then those might be a 10 power minus 4 range. Again, this will also be in a 10 power minus 4 or 10 power minus 3 range. This would be a 10 power minus say 6 range. These are all weak acids. The K values, these are the K values. What do we mean by the K values? It depicts how much of ionization has happened. So we'll be doing that. We'll be doing the law which will give you the K value, the Ostwald's dilution law. So we'll be doing that a bit later. Weak bases would be your ammonium hydroxide, your amines, your anilines, your pyridine. Now you don't have to know all these. I'm just listing it. You don't have to. Whatever weak base is given, it will be given to you with a K value. Just for your GK, what are your amines? What is this? In fact, what is this? This is NH3 when it is aqueous. When water has attached to it, it is aqueous. NH3 is NH4OH. So your NH3 is a weak base. When you replace your H and you put a carbon chain to it, I'll call it as a R. So in your NH3 I have kept two H's, but one H is replaced with a R. That's an amine. What is an aniline? It is a very similar thing. Your one H has been replaced by the benzene ring. So that's an aniline. What is a pyridine? Pyridine is again, you have a N which is going to complete the structure which is similar to a benzene ring, but instead of a C, it is an N which is completing the cycle. So that's your pyridine. So these are your weak bases, and we don't have to worry about the structure and all a bit. We don't have to look into all this. You don't have to worry about all this at all. Your K value will be given to you, or you might be asked to calculate it, and the compound would be given. You would be knowing what you are doing. When we get into the chapter, you'll understand what it is about. So this page is just a list of the electrolytes, and when the chapter is going on, you might be encountering these chemicals mentioned, and it is going to give you some confidence that you have seen these compounds when we have started this chapter. So that's it about your strong electrolytes and weak electrolytes. Let us now continue and understand what an acid is, what a base is. What do we mean by an acid? What do we mean by a base? So long back, it would have been something which is corrosive, something which is sour in taste, is acidic. That would have been your acid. But then we have a modern definition for all these things. So we'll see what an acid is, what a base is, what qualifies for that. All these things are getting into this chapter of ionic equilibrium. We should be knowing all this before we start into the main core aspects of ionic equilibrium. After knowing what's an acid, what's a base, I'll be telling you a lot about what is water. If you understand water well, and then all of these would be dissolved in water, you'll have aqueous solution. So if we understand water well, we are going to understand the equilibrium it would be holding, and it will be helping these guys to hold with each other. So understanding water would be quite interesting.